Hello students, in this video we'll discuss determinants in higher dimensions using cofactors. So let's recall that we have determinants defined for two-dimensional matrices by this result. A, B, C, D is AD minus BC. And we defined a three-dimensional determinant by the following cofactor rule, which we didn't explicitly mention, but that's what we were doing. A1, A2, A3, B1, B2, B3, C1, C2, C3 by what? By, it was A1 times the determinant we get when we punch up the row in column, so that's going to be a B2, C3 minus C2, B3, C2, B3, then minus A2 times B1, C3, B1, C3, and then C1, B3, then C1, B3, C1, B3, then finally plus A3 times B1, C2 minus C1, B2. Like that. Great. And what I really did here is I really did a cofactor expansion. So this is really a cofactor expansion. So let's see how we can use this cofactor in general. So for an n by n matrix, so let's let A be an n by n matrix. And we're going to assume that I've defined determinants at level n minus 1. So we've defined determinants at level 2 and 3. I can say that A is a 4 by 4 matrix, and I will have known how to do 3 by 3 matrices. Once I can construct a 4 by 4 matrix, I can construct a 5 by 5 matrix, a 6 by 6, I'll do it inductively. Assume that you can define a determinant for n minus 1 by n minus 1 matrices. Okay. Then what I'm going to do is I'm going to define the cofactor Cij of A is -1 to the row plus column position, and then times the determinant of A with row I and column J removed. So if you remove from your n by n matrix a row and a column, you will again have a square matrix, and that square matrix will be dimension n minus 1. So this is going to be an n minus 1 by n minus 1 dimensional matrix, and you know that you can compute a determinant for that, okay? And so now I'm in a position to define the determinant for the n by n matrix. How so? We'll define determinant of A will be A11 C11A for the first cofactor, then A12, then C12A, all the way down to what? All the way down to A1N C1NA, right? And if you want to write this in terms of these, well, let's call these matrices over here, let's call these A sub ij. This can also be written as what? As A11, let's call it determinant of A11 minus A12 determinant of A12, all the way down to -1 to the n plus 1, because I have a 1 first row and column, determinant A1n, determinant of A1n. So these things are called cofactors, as I alluded to. So these are called cofactors. And this is the cofactor expansion. So if we apply the cofactor expansion to the three-dimensional case, we'll exactly get the form that we have over here. So those are clearly now the cofactors, right? So those are cofactors over here. Excellent. Now the remarkable theorem, which is due to Laplace, is that you can compute determinant of A. Determinant of A can be computed by expanding along any row or column. Okay. Now, we'll prove that in another video. I'll give you a very, very important example of how this is helpful. So here's an example. And that is if I have an upper triangular matrix, so if A is upper triangular, then A will have what form? A will have the form lambda 1, lambda 2, lambda n on the main diagonal, zeros below it, and any numbers you wish above the main diagonal, right? Then what we can do is if there are zeros, what we'll do is, and for this matrix over here, we'll expand along the what? Expand along the first column. So this will be what? This will be a lambda 1 times what determinant? Times the determinant of another smaller upper triangular matrix, lambda 2, all the way down to lambda n with entries above it and zeros over here. And then we can expand this determinant along the first column again, right? Everything else is going to be 0. And so systematically by induction, what we'll get is we will get lambda 1 times lambda 2 times all the way down to lambda n. And this is going to be a very important fact for us, is that when we're computing the determinant of an upper triangular or a lower triangular matrix, we'll just have to multiply the diagonal entries to get the value of the determinant. So that's a very useful calculational tool, and it follows from this Laplace theorem that you can expand the determinant along any row or any column. Thank you very much.